December 22nd, 2015. Guys, I've been trying to put this video together for a few days, but each time I went into the information, I found something else that I wanted to research and try to make it as complete as possible. And I did get some information that may help quite a bit, but I'm going to need help by someone that's very good at putting this into the astronomy models and the solar system models to try to figure out the orbit. Now, what you're looking at on the left, July 7th, 2014, in band 7, you're looking at, I think it's Alpha Centauri and A and B. You can see that in the bottom. U represents this unknown object that's entering the solar system. Now, one thing about it, they caught two different trajectory points in July of 2014. So this last photograph on the right, May the 2nd of this year, in what's called band 8, you can tell it's closer because of the grains are larger in the imaging. But the object above Alpha Centauri A has moved to the left and down. You can tell that quite a bit. Now, what's important is in July they had two readings. Now, they had two readings in this. The image on the right, again, you can tell it's closer. Band 8 is this year, May the 2nd, 2015. You can notice that the object appears closer, and it's more directly over Alpha Centauri, just below it. Now, also, you got to remember that the imaging from the Earth changes as the Earth rotates, the angles and things like that. But again, it shows a difference. Now, what we want to do is, using some people that are good at putting this into the model, is take this May 2015 information and tie it in with the 2 points from 2014, and let's look at that. Now, I will link to the different documents that I'm using, but this is all from, again, ALMA. This is the giant observatory in Chile, but they're calling the object GNA. GINA, we can call it that, or GINA. But the properties are, you look at the epoch date, March 20th, 2014, April 14th, 2014. See those two dates, and then it gives you, with the hours and minutes and seconds, the declination and the flux. They had went into this chart, and they were going to get a third one in, again, May of the 26th of 2014, and it had moved out of the range where they had focused to get that third epoch date. Now listen, what that could possibly mean, and probably does, is it's moving faster than they thought it was, because they did not have the information that they do now with that new photograph from 2015. And I'll try to get as much information into this video from that photograph. But they're talking about, they're looking at the 3 different scenarios of what the object could be. And most of the information came out before we have the new photograph. So I don't have the updated data from these guys that saw this from the, again, from Chile, from the ALMA observatories down there. I think it's, remember, 66 big satellite dishes. Then they're tied in with one in North America and one in Spain, I believe, and it makes the largest telescope in the world as a combine all of that together. But again, let's look at some of the other data here, and again, we're going to need help on this one. Now, for you guys that are going to try to model this, you'll have to pause it and absorb the data. That's what it takes. It's what I had to do here. But again, I'm not professional at the modeling, but here's what we've got. Notice it's the new solar system object discovered with ALMA at the top of this. This is a PDF. I will link to it. And they've got, remember, they could not determine the distance, and we were trying to determine the velocity. And as I think back about the first video, we need the distance to determine the accurate velocity, is because they were looking at the background movement. Remember that? But what they're thinking about here, the 2 dots in the center are the 2 sightings. This was in July, are the 2 radar images. But at 20 AU is what they were thinking. Now, that's the closest point. And if that were the situation, we would be looking at the orbits there. And you can look at the arc seconds, both in the going vertical and horizontal here. So you can add this information. Notice we're talking about 10 kilometers per second is what they're estimating. But if I pull this down, and we'll bring it up. Now again, pause this and so you can go back. It's a lot of information. I had to bring this up so we can at least try to read this. But it's saying in the top figure that we just looked at, this is the potential trajectory of motion of GNA based on the two ALMA detection solid dots. Remember, these are the two in July, not this year. Excuse me, 2014. The dash square indicates the size of the third ALMA epoch mosaic in which GNA was not detected. Remember, I said that it was moving so fast that they didn't pick it up until this year. The black solid line is the orbit for a source distance of diameter of 20 of 20 AU. The green short dashed line has a distance of 2000 AU. The blue dashed line represents a distance of 10,000 AU. And the red long dashed line constitutes a distance of out to 25,000 AU. On the orbits, the open circles indicate the expected position of the epoch of the third ALMA observation. Now, for the source at 20 AU, that's the outer distance, the expected position lies more than 1 degree outside the figure, and that's the one above. And the arrow denotes the proper motion, and that's what we looked at, remember, in the first video. Proper motion scaled so that 1 inch equals 2 kilometers a second for each of the different orbits. I'll pull that back up again, but guys, you'll have to pause it. Here's the diagram. Now, guys, I've watched some of your videos, and you're very good at putting this information into models. You've done that very well. I've seen it. I don't always comment on your videos, but I do pay attention to it. So step in there and take this and see what you can do with it. Let's look at a couple other things. Now, this diagram may help somewhat too. You notice on the left side of the column, it's giving you the velocity in kilometers per second. And then AU on the bottom from 0 up to 50 AU. And we looked at that up to about 20 AU on the first video. I'll show you that diagram. But it gives you, notice, your different legend here for the different objects or the different orbits of this object. And we'll look at the information. But again, don't forget, I'm going to link the PDF because there's tons of information that may put some connection in there for you that I'm not presenting here. Now, what they're saying in the chart I just showed you is the Keplerian velocity for gravitationally bound solar system object on a circular orbit, and that's what we're trying to determine, which is the solid black line, and the maximum velocity at perihelion. You know, that's when an object comes in, and you'll see it very fast, but it will speed up those last few days before it whips around the sun in that slingshot motion. Now, they don't know if that's going to be close or far away. We're trying to determine that, but they do think it's going to have an inner solar system perihelion. It says for gravitationally bound object on an elliptical dotted red dash blue line, and that's in the chart, and long dash green lines, which are the orbit with different eccentricity. The velocity is given as a function of semi-major axis A. The horizontal dash line indicates the measured velocity of GNA. The symbols indicate the perihelion distance at which the observed velocity corresponds to the orbital velocity for the circular and the 3 elliptical orbits. The circle denotes the circular orbit. The triangle, the elliptical orbit, and at E equals 0.25. The square, the orbit with E equals 0.44. In the pentagon, the orbit equals 0.95. Again, this is slightly above my pay scale, I promise you, but there's people out there that can do this. Now, for the 2014 sightings, we have this information. I don't have this or haven't found it yet for the 2015 that we have in the photograph, but these are the two ALMA detections on March 20th, 2014 on the left and April 14th, 2014 on the right. It gives you your declination offset in arc seconds and your RA offset in arc seconds on the bottom scale. Now, you can read through this and get the technical information, and because it is very technical, it's not going to do me a lot of good to read this. You can pause it and read it yourself. Again, guys, if you go into this and you get some information, bring it back and do a video, whatever you want to do, or send us the information. We'll do the video or link to yours, and let's try to find this orbit. Let's look at that 2015 image one more time. Again, here's the image. Notice at the top Centauri, and you've got the last reading here, July 7th, 2014, and then the last reading this year, May 2nd, 2015, guys. Now, I'll also give you it's a brief paragraph of the information about this particular image, so use this also. Now, this is going back to the information that we had in the last video, but we can add that new image, and this talks about the new image. And you notice it's Cornell University Library, and that's where they're sending this information in. I'll pull this up, and again, use this to pull the info from the photograph that includes the 2015 image. We recently announced the detection of an unknown sub-millimeter source in our ALMA observations of Alpha Centauri A and B. The source was detected in 2 epochs, a strong detection at 445 gigahertz and one at lower significance at 343.5 gigahertz. After valuable feedback of the community, it turns out that the detection at 343.5 gigahertz could not be reproduced with a different reduction software, nor with fitting within the UV plane. The detection at 445 gigahertz has been further confirmed with modeling of the UV data and was shown to be robust. It says, however, based on only one epoch, further analysis and preferably new data are needed before publication of an article in which the nature of the new source can be discussed. The analysis has indicated the importance of both the UV plane fitting and alternative data reduction when dealing with low signal to noise source detections. Now, I used this chart in the first video also. Let me pull this over just a little, guys. But it gives you some different information. First, they're looking at around 20 AU at this object. Now, if you remember in the video, the first one, it said they were looking from 12 to 25 would be the average, and I noticed them focusing on 20. But anywhere, what you're looking at is Saturn is 9.5 AU away from the sun. If you look at that image in the top left, and then the 29 means it takes 29 years to orbit the sun. If you go all the way down to the bottom left, you can see Mercury is at 0.3 AU. It takes 0.24 years. Go up to Earth, you can see 1 AU, and that's where the AU is based at. 1 year to orbit. But the object they're looking at, they think is between Saturn and Neptune. But until we know the orbit, we have nothing really to go on. That's why I'm putting out this information, guys. If you can help, do it. This is a heads up. Be safe.